In this opportunity, we're going to talk about the Gibbs free energy, which is another thermodynamic property, and as such, it's going to be a function of state. If you remember, functions of state are kind of properties that depend on the final and initial state of a particular system. The enthalpy is a function of state. The entropy is also a function of state. And the Gibbs free energy is a third one that we're going to be using to predict spontaneity of reactions. So it's the one that we will actually use to predict spontaneity, not only the entropy of a system or surroundings, which it controls the spontaneity of the a process, but if you also remember at the beginning of this chapter, when we refer to spontaneity of a reaction, it depends on both the enthalpy and the entropy of that reaction. But the Gibbs free energy involves those two. So if we wanted to define the Gibbs free energy, basically is the maximum amount of energy that you have available to release to the surroundings. So, and it depends on both the enthalpy and the entropy of the system. And it's an equation that you should get familiar to use, okay? It's also referred to as the chemical potential, but so those definitions are not something that you have to worry too much. The point is that the Gibbs free energy is a thermodynamic property that we are going to be using to predict spontaneity of a reaction, and there is not much more to it than that. Now, this is an equation. It's an equation that relates the free energy with the enthalpy and the entropy of the system, the changes in enthalpy and the changes in entropy of the system. And one interesting thing that we may do with this equation is, well, it's not an equation that comes out of thin air. It's something that comes from another more concept that we have reviewed already. And if you remember, the second law of thermodynamics is telling you that the changing entropy for the universe is going to be equal to the changing entropy of the system plus the changing entropy of the surroundings, correct? So if we start with that, we have that the changing entropy of the universe is equal to the changing entropy, not the energy, entropy of the system plus the changing entropy of the surroundings. But based on our previous videos, we remember that the changing entropy for the surroundings is equal to minus the delta H, the changing entropy for the system, divided by T. So we can take that equation, we can take that expression here and substitute it here. Therefore, the changing entropy for the universe is now the changing entropy for the system minus delta H, changing enthalpy for the system, divided by T. And the interesting thing that we are going to do with this is that we are going to multiply all of these by minus T. Okay? Therefore, we will end up with minus T changing entropy of the universe is going to be equal to minus T changing entropy of the system plus delta H of the system. Okay? This quantity that you see here, the changing minus T changing entropy of the universe, that is our delta G. That's delta G. And here we have the changing enthalpy for the system and minus T delta S for the system. Okay, so this is where that equation comes from. So we are just defining the changing free energy of the system as minus T changing entropy of the universe. Okay, so, and here one of the things that you remember according to the second law is that if the changing entropy for the universe is positive, then the system is, the reaction, the process is spontaneous. However, with this negative sign here now, if the change in entropy for the new universe must be positive for the process to be spontaneous, well, with that minus there, then the delta G has to be negative. Okay? So out of this equation now, delta G, if it's negative, then is spontaneous process. Okay, and this equation right here conveys the information that we were giving at the beginning, that the spontaneity of the process depends on both the enthalpy and the entropy of that system. So both factors here are used in this equation, and effectively then now with the value of delta G we have something more quantitative, okay, to predict spontaneity of a reaction. We can measure the enthalpy, we can measure the entropy, we can calculate delta G, and then according to the sign of delta G, then you can predict spontaneity of a process. Okay, so it all reduces to, well, when is delta G negative, when is delta G positive? Okay, as said before, delta G must be negative for the process to be spontaneous. Okay, and whenever you are doing this analysis, just refer to the equation, correct? So delta G, and let's use a simplified version. Delta G equals delta H minus T delta S. So when is delta G negative? Okay, so if this is negative, and with the negative sign there, if this is positive, and no matter what you do, that delta G is always going to be negative. Okay, so it's going to be a process, spontaneous process, when always a spontaneous process when delta H is negative and delta S is positive. Okay, but now you may have these situations as well. What if delta H is negative and delta S is also negative? Okay, see, if delta S is negative, then it depends on the temperature. Okay, so meaning if delta S is negative, then it depends on the temperature. Okay, because this term is going to be positive, so in that case the enthalpy has to be large. Okay, and as long as delta S is small enough, then you still get a delta G that is negative. Okay, you can have the opposite situation in which delta H is positive, and if delta S is positive as well, then it has to be large for delta G to be negative. So this is kind of a game of words here. It might be a little confusing, but this is something that you need to master. Let's put it that way. Look at the equation and then determine when delta G is going to be positive and when is when it's going to be negative, and that is just by changing the signs. So it depends on the signs and the magnitude of the values of delta H and delta S. Okay, so this is, remember, we are interested in delta G negative because it tells you when a process is spontaneous, and delta G positive is going to be a non-spontaneous process, and then same thing, you have to determine when delta G is going to be positive. Okay, so for example, if delta H is positive and delta S is negative, then delta G is always positive. Let's add that. It's always positive. Okay, and then if you play with the signs and the values, then you can have situations in which delta G is going to be positive and delta G is going to be negative. Okay, so the word game here, it might get complicated. So we can also do something that is a little probably easier to remember. We can summarize that information on the table. Okay, and again, remember the equation. Delta G is equal delta H minus T delta S. Okay? So here we have the signs. If delta H is negative and delta S is positive, the process is going to be spontaneous no matter what you do. Okay, this is going to be negative, this is going to be positive, which means the whole term here is going to be negative. No matter what you do, delta G is going to be negative. So when you have this combination, and let's pick it up. So if we have this combination here, okay, you notice that we have low and high temperature and it's going to be spontaneous. The other way we can say this is spontaneous at all temperatures. Okay? Let's go to the opposite case. In the opposite case, we have if delta H is positive. Okay, now it's the opposite thing, right? So if delta H is positive and delta S is negative, then that term is always positive. Okay, minus T, okay, again, minus T delta S, if delta S is negative, that is going to be always positive. Then delta G is always positive, no matter what you do. And in this case, you say is non-spontaneous at all temperatures. So you have a situation that always spontaneous and always non-spontaneous. Okay, and then you have the cases in between. If it's negative, if both are negative, then you have a process that is spontaneous at low temperature and non-spontaneous at high temperature, and vice versa. Okay. Now, what does it mean by low or high temperature? Well, it depends on the system. Okay, do not follow what you believe is high temperature or low temperature. It depends on the process. For processes, high temperature could be minus 20 Celsius degrees. For other processes, low temperature might mean less than 800 Celsius degrees. So it depends on what the process is. So do not follow your thermal sensation to determine what is low temperature and what is high temperature. It will depend on what the process is. Okay? Let's start doing some exercises with this so that this becomes a little more clear. So we have this problem here, right? So in this case, we have the reaction, we have our delta H, and we have our delta S. And if you notice, they are both positive. Okay, if we go back here, they are both positives, which is the case that we have in hand here, we are looking at a process that is non-spontaneous at low temperatures and that is going to be spontaneous at high temperatures. Okay. So let's do the first thing. We have to calculate delta G at 25 degrees. Okay, and delta G is going to be delta H minus T delta S. That temperature has to be in Kelvin degrees, so not Kelvin degrees, just Kelvin. So temperature is equal to 25 plus 273, which is 298 Kelvin. Okay, and then one other thing that you need to notice here is that the units of delta H usually comes in kilojoules. However, the units of delta S usually comes in joules. So you either convert to joules or convert to kilojoules. So how about we take this first to joules? So 95.7 kilojoules is equal to 95,700 joules. And this is plus. Okay, it's a positive sign. So therefore here, delta G is going to be delta H, which is plus 95,700 joules minus 298 Kelvin times delta S is also positive, and this is 142.2 joules over Kelvin. Here we cancel kelvins and we end up with units of joules. So out of these we obtain 53,300 joules. And let me just double check this calculation here. So 298 times 142.2. Okay, so this is about what we get, and this is positive. Okay, so since our result, and we can take that back to kilojoules, so since delta G is equal to plus 53.3 kilojoules, then this means the process is non-spontaneous. Okay? So, if we remember here, okay, we were in this case, both the delta H and delta S are positive, so the process is non-spontaneous at low temperature. It will be spontaneous at high temperature. Okay, if we keep increasing the temperature, then the process will become spontaneous. And now, how do we determine what the temperature is? At what temperature the process will become spontaneous? Then that's the second question here. Okay, the process is non-spontaneous, and we want to know, well, at what temperature that process becomes spontaneous. So the first thing that we have to do here is we're going to make not delta H, delta G. We're going to make delta G equal to 0, and that's still equal to delta H minus T delta S. However, in this case, because they are equal to 0, okay, by the way, delta G equal to 0 is equilibrium. Remember, you have a forward reaction, and then you have the reverse reaction, so to speak. So basically, at that point where the system is in equilibrium, then you switch from a non-spontaneous process to a spontaneous process, or vice versa. Okay, so delta G equals 0 marks the temperature at which the process will change from spontaneous to non-spontaneous, or from non-spontaneous to spontaneous. So in this case, they are equal to 0. Therefore, delta H is going to be equal to T delta S. And finally, the temperature is going to be the ratio between delta H and delta S. So that's all we have to do here. So that temperature is going to be equal to, and let's convert that again to plus 95,700 joules divided by 142.2 joules per Kelvin. Here the joules cancel with each other, and out of this reaction, out of this calculation, we obtain that that temperature is going to be equal to 673 Kelvin. Okay, so at that temperature, if you keep increasing the temperature, the process becomes spontaneous. Below that temperature, then the process is non-spontaneous. Okay, so then for this particular system, low temperature means less than 673 Kelvin, and high temperature means more than 673 Kelvin. Okay, even low temperature is pretty hot for one, right? For any of you, but remember, low temperature, high temperature depends on the process, not on your thermal sensation. Now, in this particular case, well, Now we have a case in which both are negative. Okay, so if we go back to our table, now we are in this situation. Both are negative, so we are looking at a process that is spontaneous at low temperature and a process that is non-spontaneous at high temperature. Okay, so first things first, so we are to calculate delta G at 25 degrees. So 25 degrees is 298 Kelvin. Therefore, delta G is equal to minus, let's put that within parentheses, 137.5. Let's keep kilojoules this time. That means this becomes minus 0.1205 kilojoules per Kelvin. That's just to show you that you can use kilojoules or joules. Okay, it depends. It's up to you what unit conversion you use here. So this is kilojoules minus 298 Kelvin times minus 0.1205 kilojoules per Kelvin. So in this case, we cancel the kelvins, okay? And we end up with a value that is minus 101.6 kilojoules. As such, it's negative, okay? So therefore, delta G is less than 0, and this process is spontaneous. Which means at that temperature, at 25 degrees Celsius, this process, whatever the reaction is, you don't really care about what the reaction is actually, but that reaction is going to be spontaneous at that temperature, okay? Now the next question is, does delta G become more negative or more positive as the temperature increases? Okay, and one thing that you have to notice here is that you have a negative sign here and a negative sign there. Okay, the value of delta S is going to be constant. The only thing that you are doing here is increasing the temperature. So if this if this temperature increases, what is going to happen? Well, what is going to happen is that value is going to become more positive, more and more positive. And if it becomes more and more positive, then the delta G is going to become more and more positive. So that means if the temperature increases here in this particular process, then delta G becomes more positive, okay, up to the point in which it will become non-spontaneous. Okay, what temperature that is? Well, we don't know. We haven't calculated that. We don't really need to calculate it, but because there is another question. But what if we do it? Okay, so we have all the information that we need. Delta H is minus 137.5 kilojoules. Delta S is equal to minus 0.205 kilojoules per Kelvin. Therefore, if delta G equals 0, then delta H is equal to T delta S, and therefore temperature is delta H divided by delta S. So therefore that temperature is minus 137.5 divided by minus 0.205 kilojoules per Kelvin. The kilojoules cancel, and the result that we obtain here, just give me a second, 137.5 divided by 0.1205, this is equal to 1141 Kelvin. Okay, a big change here actually if you compare that to the other process. In the other process, it will become spontaneous at 673 degrees. This would you have to go even higher to a temperature of 1141 Kelvin in order for that process. In this case, delta G is going to become positive, so the process will become non-spontaneous. This is non-spontaneous at low temperatures. It will be it will be spontaneous. Spontaneous at low temperature. It will become non-spontaneous at high temperature. Okay, so this is how you calculate delta G if you have the proper information.